Hi everyone, my name is Óscar Carrión-González and I am about to finish my PhD at TU Berlin, where I've been mostly working on direct imaging observations of exoplanets in reflected starlight. This means in the visible and the near infrared wavelength range. But as part of the LIVE mission, I'm also quite excited about this mid-infrared approach. And I will be talking about a preliminary work that I'm doing with Jens Kammer and other colleagues of the LIVE collaboration, where we are trying to understand which are the possible synergies between future direct imaging instruments observing in reflected starlight and the LIVE mission. Let me maybe start from the very beginning, which is why all this excitement about direct imaging. The issue here is that current observations of exoplanets are dominated by the transit technique. And this is biasing, just due to the technology available right now, this is biasing the population of exoplanets that we have detected and characterized towards warm and hot planets in short period orbits, and all these outer companions which are not likely to be found in transit. Well, all these planets are right now hopeless for atmospheric characterization. And the only chance to characterize the atmospheres of all this population of cold and temperate long period planets is to actually get direct imaging observations of them. And we will be achieving these direct imaging observations by suppressing the stellar glare with optical devices such as coronagraphs or star shades, or by means of optical methods such as the nulling interferometry, which is the approach taken by LIVE among other instruments. So we have a pretty exciting direct imaging timeline in the short and long-term future, in which we will be pushing towards better sensitivity of the instruments until reaching the ultimate goal of observing Earth-like planets around sun-like stars. Right now, direct imaging means observing young giant exoplanets in emitted light. This means we are observing very far out companions in very early stages of formation. This will change with the launch of the Roman Space Telescope with its coronagraph instrument. This will enable finally reflected starlight observations of cold, mature exoplanets. At the beginning, this will be giant planets, so probably Jupiter analogs, because these are the easiest targets. But with future telescopes like LUVOIR, HabEx, or LIVE, we will get down to the low mass planet regime, including several potential Earth analogs. So all these missions will have different approaches, but very similar scientific goals, which are ultimately understanding how unique is our solar system, how unique is our Earth, and how unique are the atmospheric conditions that ended up harboring life in our planet. And Roman, HabEx, and LUVOIR will try to assess this by observing in the visible and near infrared wavelength range. LIVE will do this in the mid-infrared, and each of these wavelengths will probe different properties of the exoplanets and their atmospheres. So for instance, visible reflected light observations might be very useful to characterize the aerosols in the atmospheres of these planets, while mid-infrared measurements could help in constraining the planet radius if these planets are not transiting, and also getting the temperature profile of these planets. Also, as shown in this slide, you can see that the mid-infrared has a lot of absorption bands from very interesting molecules such as water, CO2, methane, ozone, and so on. So the ultimate goal is to observe an exoplanet both in reflected starlight and also in the mid-infrared thermal emission. So we want to make sure we have targets that overlap, that are accessible with both techniques. And this is what we are studying here. This is what I will be talking about. We want to understand what is the overlap between the exoplanets that could be detected with the reflected starlight telescopes and with LIVE. And to compute the exoplanet detection yield of an instrument, we have generally two approaches. The first of them, which has also been implemented for life, is to get a stellar catalog as an input and create synthetic artificial populations of exoplanets by using planet occurrence rates, for instance, from those discovered with the Kepler mission. And with this, we create these synthetic populations of exoplanets. We assess the detectability of each of these simulated targets, and we yield predictions of the detection yield with several scenarios or different instrument configurations. And this allows us to get a feeling of which populations of planets are more likely to be observed or more favorable for a particular instrument. The second approach towards understanding the types of exoplanets that a mission could observe is to actually use the population of exoplanets that has been already discovered. And this, of course, will miss the many exoplanets that are yet to be discovered, but this gives us lists of potential targets that are already confirmed, and this gives a more concrete feeling of the possible science cases that a mission could address. We have developed a statistical methodology for this latter approach, which is the one that we will be taking in this work, and this methodology basically consists on downloading the NASA Exoplanet Archive database and running thousands of orbital realizations for each of the known exoplanets by letting each relevant parameter vary within its reported upper and lower uncertainties. So at the end, we have an output catalog of exoplanets that could be accessible with a particular instrument. We published this methodology earlier this year in a paper where we apply it to the Nancy Grace Roman Space Telescope in order to build lists of potential targets of which are Roman accessible. This means which at some point orbit within the inner and the outer walking angle defined by the coronagraph and are also brighter than the minimum contrast of the instrument. And these general considerations will apply to all the other reflected starlight telescopes and indeed any other direct imaging mission. That is, we divide each orbital realization into several positions, and at each orbital position we check the brightness of the planet and its angular separation. If both are within the operating requirements of the instrument, we say that this planet at this position will be accessible to that instrument. And the theoretical setting is quite simple. We compute the angular separation between the planet and the star by means of Keplerian equations of motion, and also to compute the brightness of the planet in reflected starlight, we will need to take some assumptions, such as the geometrical albedo of the planet that we take to be 0.3, rather conservative value. In order to compute the brightness in the mid-infrared in thermal emission, we have to compute the equilibrium temperature of the planet at that orbital position, for which we assume a Born albedo of 0.45. And by letting the planet orbit, we will be observing different changes in the brightness and the angular separation, depending on how far it is from the star and how the equilibrium temperature changes, and also on how the phase angle of the exoplanet changes and it is reflecting more or less light towards the observer. A novelty of our method is that it supports a just partial knowledge of the orbital information of a planet. That is, not all of the known exoplanets have a constraint on the orbital eccentricity, on the orbital inclination, or on the argument of periastron of the planet. And in these cases, we draw at each of the thousands of orbital realizations, we draw a value for these unknown parameters within this from these probability distributions that I am showing here. It also supports the fact that the planet radius is unknown. For that, at each orbital realization, we compute it by means of published mass radius relationships. So with that, we produce a set of outputs. First of all, the probability of the planet to be accessible, but also other parameters which are useful for atmospheric modeling studies, such as the range of phase angles that the planet is observable, which is useful for reflected starlight observations. And also we compute how the equilibrium temperature varies throughout the orbit, which is also pretty useful for mid-infrared measurements. We also compute the time that the planet remains observable, which is relevant to compute the possible signal-to-noise ratio that we could get to achieve. So for reflected starlight missions, we get the different relevant parameters of the instruments, that is the diameter of the telescope, the inner and the outer working angle, and also the minimum contrast of the instrument from the corresponding mission reports. For live, we use LiveSim, the detectability simulator of the mission, by providing it with the equilibrium temperatures of the planet that we computed with our methodology. We assume an observation at quadrature, and with that we run LiveSim to get a list of observable planets. And I have to note here that LiveSim does take into account more considerations, such as the stellar leakage due to the angular separation between the planet and the star, and also local zodiacal light and exosoldi. So it provides a rather complete simulation of the nulling interferometry that would be launched to space. And this is a bit more complex than the considerations that we take for reflected starlight telescopes. So when we say that a planet is accessible in reflected starlight, say with Roman or with HabEx or LUVOIR, we will be referring that it is within the operating range given by the minimum contrast, the inner working angle, and the outer working angle. But we are not considering additional noise sources or other factors, because we do not have detectability simulator tools for each of these missions. So in this case, a planet accessible in reflected light does not mean it will be detectable for sure. It is potentially detectable. Also, let me note that in a second I will be showing the results, and in these plots I will only include as detectable the planets with a probability of being accessible greater than 25% to avoid somehow residual cases. But as I was mentioning, when we assess the detectability with live, we are taking into account many more factors. And indeed, when we say a planet is accessible, observable with live, we mean that it requires less than 100 hours for an observation to get a signal-to-noise ratio of 7, again, by accounting exosoldi levels, the local zodiacal light, and so on. So here accessible means actually detectable with live with all these considerations. Let me then show you some of the preliminary results. These are the overlapping targets that could be observed or that are accessible with live, and also some of the reflected starlight telescopes that we consider. Again, Roman, HabEx, LUVOIR-A, and LUVOIR-B. So planets with a marker in yellow means that they are detectable with all of these missions. These are pretty accessible target, good for benchmarking. When you see a marker in dark blue, this means they are only observable with live and one additional reflected light telescope, generally LUVOIR-A. And you can see that the population of planets that is overlapping does change if these are nearby, that is closer than 10 parsecs. These are in this region we are sensitive to low mass exoplanets, but if we move a little bit farther out between 10 and 20 parsecs, we are just sensitive generally to giant exoplanets, very massive planets. We also find an interesting population of planets which are not accessible in reflected starlight, but detectable with live. And this is it. Each of these points is a known exoplanet. So all of these have names, and you can find several of them in this temperate terrestrial regime, potentially in some mass regime similar to that of the Earth, and with equilibrium temperatures in the same range. So we conclude from this that life is actually more sensitive to finding and detecting rocky temperate exoplanets. So by computing which exoplanets could be detected by each of the missions, we are also computing statistics on the host stars that we will be probing. So we are also accounting for this in this study. Of course, if life probes more planetary systems, it will be probing many more stars than the others, particularly many more M stars. As you can see, we also build statistics on the age of the stars, their mass, and also their brightness. So this is another thing we will be considering. This is also something to get potentially feedback from the live community to check which are the most interesting science cases. So let me summarize this all. We have built target lists for live. This is pretty useful to start defining which are the potential science cases that we could address with this mission. But we have also created target lists for Roman, LUVOIR-A, LUVOIR-B, and HabEx, and we have created them all by using the same methodology, so the comparable and consistent method. And this is potentially interesting for people outside the live community as well. We have studied the synergies between reflected light and emitted light missions, and we have also computed which planets are only accessible with live. In future work, we will be refining and updating all these previous results, but we will also be addressing which transiting exoplanets are accessible with live, which this means which transiting exoplanets could also be observed in direct imaging of thermal emission with live. We have potentially several of them, so this is good news. We will have to keep working on this, but prospects are encouraging for this, and we will also be addressing which science could we perform on young subluminous planets, namely some of the ones that we have already discovered in direct imaging of emitted light. So with that, I'll leave you my contact here. You can also reach me on the Slack channel. Please get in touch if you have any comments or questions about this. Thank you very much.